In this video, we are going to look at how to represent a system of linear equations with a matrix and the echelon form that we want to get the matrix in so that we can solve the equations. We will start by representing the system of linear equations with a matrix and then using elementary row operations to get the matrix in echelon form, which looks like this upper staircase that similar to what we did in the previous video. We have a couple of theorems to relate these matrices and the system of linear equations, and then finally we'll go through a couple of complete examples. To represent a system of linear equations with a matrix, we simply take the coefficients and we have a coefficient matrix. So the first row is the coefficient of the first equation, which is 1, 2, and 1. The second row are the coefficients of the second equation, which is 2 minus 1 minus 1. And the last row is the coefficients of the last equation, which is 1, 1, and 3. So here is the coefficient matrix, and then we put the vector b, the 4, 1, and 0 over here, and with that we get what we call the augmented matrix. So B is the augmented matrix, and that is the augmented matrix consists of the coefficient matrix plus the solution 4, 1, 0 over here, which we will designate with B. And now we can define elementary row operations, which are the same exact operations we used to do on our linear equations. That is, we can interchange two rows of our matrix, just like we used to interchange two equations. We can multiply a row by a non-zero scalar, just like we used to do with our system of equations, and we can add a constant multiple of one row to another, as we had done before. And again, this should all be familiar, or the reason why it's the same operations is because essentially we're just representing this system of linear equations with this matrix. So the operations we do will be the same. And we are going to use those row operations to get our matrix in echelon form. And roughly speaking, echelon form means we have an upper right-hand staircase or triangle. So here is a matrix in echelon form, and by staircase, that's like this blue line, and it separates these zeros from these other coefficients. Or the triangular, the upper triangular form, I have that outlined in green, so I can kind of put these coefficients here, the non-zero coefficients, and outline them with a triangle. So that's the idea here, is that you have this upper right-hand triangle or you have this upper hand staircase. Formally, echelon form is defined as follows. All rows that consist of entirely of zeros are grouped together at the bottom of the matrix. Here we don't have any rows of entirely of zeros, but if we did, we would just put it at the bottom. And then the next condition is the first, and by we're counting from left to right, non-zero entry in the I plus first row must appear in a column to the right of the first non-zero entry in the ith row. So if we look at the first column, well, we don't want to do that. We want to get to the I plus 1. So if we look at the second column, its first non-zero entry, which is 1 here, must appear to the right of the first non-zero entry in the ith row, which it does because the first non-zero entry in the previous row is over here, the 3. So this, for the next row, the first non-zero entry appears to the right. For the third row, its first non-zero entry must appear to the right of the first non-zero entry of the second row, which it does because this 2 appears to the right of the 1. And then our last column, our fourth column, its first non-zero entry must appear to the right of the first non-zero entry of the third column, which it does because the 4 is to the right of the 2. So this is what it is to be in echelon form, and this is so echelon form of a matrix. And it's exactly the same sort of form we wanted when we were solving linear equations, when we were using Gaussian elimination. So I'll give you an example of this. Suppose we want to solve the set of linear equations x1 plus 2x2 plus x3 minus x4 equals 1, x1 plus 2x2 minus x3 plus x4 equals 5, and minus x1 plus x2 plus 2x3 equals 0. We can now represent this system of linear equations by this matrix here. I just took the coefficients 1, 2, 1, negative 4, 1. So that's my 1, 2, 1, negative 1, 1. My coefficients 1, 2, negative 1, 1, 5. 1, 2, negative 1, 1, 5. And negative 1, 1, 2, 0, 0. So negative 1, 1, 2, 0, and 0. And now I'm going to do those same row operations that we did with equations. So I'm going to substitute R2, the second row, with R2 minus R1 because I want to get a 0 here. So R2 minus R1 you can verify for yourself, but it'll give you 0, 0, minus 2, 2, and 4. Now I want to substitute the third row, R3, with R3 plus 1, and you can verify that'll give you 0, 3, 3, minus 1, 1. And now, again, just like I had done with my equations when I did my Gaussian elimination, I'm going to swap row 2 and row 3 so that I can get this kind of staircase. So I'll have the 0, 3, 3, minus 1, 1, and 0, 0, minus 2, 2, and 4. So this is my final form because I'm an echelon form. Here is my staircase that separates my first non-zero entries and my 0 entries. And here is my upper triangle. Now I can convert back because I'm in echelon form. I can convert back into my system of equations. So I have the x1 plus 2x2 plus x3 minus x1 equals 1. Then I have my 0, my 3x2, 3x3 minus x4 equals 1. And my minus 2x3, 2x4 is equal to 4. And now I can, because I have extra variables, my x4 can be free. I can solve for x3, x2, and x1 in terms of x4. And then just a little sanity check, if I let x4 equal to 0, then plugging in here, I get x1 will be minus 5/3, x2 is 7/3, my x3 is minus 2, and my x4 is 0. And I can just do my sanity check by plugging this in here. x1 would be minus 5/3 plus 2 times 7/3 would be 14/3 minus 5/3 would be 9/3, which is 3, minus 2, which is 1, minus 0 will give me 1. Plugging into the second equation, I have 5/3 plus 14/3, so 14/3 minus 5/3 will give me 9/3, same as this, which is 3. Minus negative 2, that will give me 5 plus 0, which is equal to 5. And now my positive 5/3 plus 7/3 is 12/3, which is 4, plus negative 2 times 2, which is minus 4. That will give me the 0. So my sanity check has kind of checked all my work for me. This example is the one that I have on my initial overview page. So here's the example here, and I just wanted to look at this example in terms of this theorem, just so we can talk about the theorem for a minute. So first we had the system of linear equations, and we converted it into a matrix representation. Then we have this theorem that says, let B be an M by N matrix. So here we have a 3 equations, 1, 2, 3, 1, 2, 3, 4, 4 unknowns. Then we can find another, and it's augmented, so we have this extra row here, or extra column here. Then there is an M by N matrix C, and that's this matrix here, C, and again, same number of rows and columns, and then our augmented matrix, such that 1, C is an echelon form, so we talked about this being an echelon form, here's the staircase, and 2, B is row equivalent to C, and these are row equivalent. What does it mean to be row equivalent? It just means that you can get from one to the other using these the elementary row operations. And then from our theorem in the last chapter, when we convert this back to a system of linear equations, what we have is any m by n system of linear equations is equivalent to some m by n system of linear equations whose augmented matrix is an echelon form. So that means this system of linear equations is equivalent to this system of linear equations. And to be equivalent means they have the same solutions. And again, I just wanted, so this is kind of the important thing, kind of going through how to solve this, but we want to see how that fits in with these two theorems. I have one more example for you. So if we want to solve this system of linear equations, x2 plus x3 minus x4 equals 0, x1 minus x2 plus 3x3 minus x4 equals minus 2, x1 plus x2 plus x3 plus x4 equals 2, we can convert that or represent this system with this matrix here. And then I'll let you verify the row operations. I switch R1 and R2, replace R3 with R3 minus R1, replace R3 with R3 minus 2R2, and I will get this echelon matrix right over here, which I can convert back into a system of linear equations. And by my theorem, this system of linear equations will be equivalent to this system of linear equations. And again, I also had a theorem that said this matrix will be row equivalent to another matrix that's in echelon form. So continuing, just to solve this equation, I can have x4 be my free variable. I back substitute to get solutions for x3, x2, and x1. And then I can do my sanity check, and I always choose my free variable to be either 0 or 1 because then it's easy, right? So I have x4 equals 0, x3 equals minus 1, x2 is equal to 1, and x1 is equal to 2. And so when you plug this in, these values into the three equations, you will see they solve the original equations. So I have nothing x2, I have x2, which is 1, plus minus 1, which is 0, plus minus 0 is equal to 0. My next equation, I have 2 minus 1, which is 1, plus 3 times negative 1, so that's negative 3, so that's negative 2, minus 0 is equal to negative 2, and then I have my 2, my 1, that's 3, minus 1, we're back to 2, plus 0 is equal to 2. And this probably goes without saying, but I'll say it anyway. While the sanity check does verify that 2, 1, minus 1, 0 is a solution to this system of equations, it is not absolute proof that your formulas here of x4 and x3 equals minus 1 plus x4, x2 is equal to 1, and x1 is equal to 2 minus 2x4 is correct. So it's not a proof that this is correct, but it does give you a really good feeling that it probably is. And that's the main points of this video. So what we looked at is using a matrix to represent a system of linear equations, to use the elementary row operations to get this upper triangular form or staircase form of echelon form of a matrix. And then we had this theorem that any matrix B can be converted through elementary row operations to a matrix C that is an echelon form. And we also had the corollary that any m by n system of linear equations is equivalent or has the same solutions as an m by n system of linear equations whose augmented matrix is an echelon form. And we used all these facts to solve a system of linear equations using matrices. As I had mentioned before in my first video, this is still sort of introductory material, which is why I'm not doing quite as many examples and we're going through it kind of quickly. But when things get a little bit harder, I will do more examples for you. But for now, that's it for this video. Thank you for watching.